So we know that a function is increasing or decreasing depending on the derivative. I have to differentiate. So I have to differentiate and then study the derivative. So what do I get when I differentiate?
So it would be 1 minus x squared
Very good.
e to the x squared.
Times x prime, but there is no need because x is 1. I mean, x prime is 1. Very good. So this is the derivative. I have to set it equal to 0 because it's always defined. This is always defined. This is always defined. F prime being undefined is not a source of critical numbers. The source of critical numbers will come, the critical numbers will come from f prime being 0. This will never be 0. E to x squared, never. So I can only get x equals 1 and x equals negative 1 when I set the only factor that can be 0 equal to 0. Very good. So then I have x. I have negative infinity to infinity, negative 1, 1. I have f prime, and I have f of x. And this is 0 and 0. I study the sign. This is always positive. I won't bother. And here, if I plug in 0, I get negative. I'm sorry. If I plug in 0, I get positive. And outside, it will be negative. So the function will be increasing only between negative 1 and 1. F increasing on negative 1, 1. Don't be afraid of a function being given in the form of an integral. It's really not something to be afraid of. Any questions? Any questions? Do you think we got the idea, or we want to look at anything else? I have 2 more topics to talk about. One topic is the second type of integral. 2 types of integrals. One that we talked about, when we'll still continue talking about, definite. The definite integral is the integral from a to b from f of x dx. Always a number. The result is always a number. The second type is what is called indefinite. It does not have limits of integration. It's the integral from f of x dx. It will never be a number, but a family of functions. Exactly the same thing with the most general antiderivative. So 2 types. This is very clear, is a number, and I can never check. I can only hope that my answer is correct. However, for indefinite integrals, we will always be able to check, because when we integrate f of x dx, and now you will see why I need that notation from the very beginning of chapter 5. What is the antiderivative of this function?
F of x.
Uppercase.
Yeah.
Very good.
Up.
Indeed. It is the uppercase f of x, of course, plus a constant c. How come that this, I claim that this I can check, but whatever, the integral from let's say 0 to 2 from x squared dx, which is x to the third over 3 from 0 to 2, which is 8 over 3, I can never check. I can only hope that this is the correct number. But if I want the integral from x squared dx, it's x to the third over 3 plus a constant c for the same function, no limits of integration, definite, indefinite. I claim that this I can check. How come? And how do I check? By something that we just studied today. Doing that to both sides. What is that I'm talking about?
Differentiating.
Absolutely. Absolutely. Differentiating both sides. And when I differentiate the left-hand side, what do I get? What do I get?
Just x squared.
Excellent. When I differentiate the right-hand side, what do I get?
X squared.
Thank you very much.
Oh.
So definite integrals can never be checked. I can only hope. But the indefinite integral, I can always check. Why? Let's check this one for the general case. When I differentiate the left-hand side, what do I get?
Just f of x. Can't see, or
Sorry. When I differentiate the right-hand side, what do I get?
f prime of x.
F prime of
right,
this
there's
x.
Lowercase f of x.
Yeah.
Yeah.
So differentiating both sides, I can always check the definite integral. Okay, so now let's practice the definite integral. And then we will look at the substitution rule. On page 404, I would like to start with number 12. On 404, and it's the integral from, x squared plus 1 plus 1 over x squared plus 1 dx. Of course, this will be a family of functions. So, which function prime is x squared? Which function prime is x squared?
X cubed over 3.
Very good. Plus x plus which function prime is this?
And
Arctangent?
Very good. Arctangent. That's it. Can you check? Yes. Differentiate this, you get x squared. Differentiate this, you get 1. Differentiate this, you get that. Differentiate c, you get 0. Differentiate this, you get the function. Any questions? Let's look at 16. Uh, 16 we have the integral from secant t, in parentheses secant t plus tangent t dt. Well, we don't know how to differentiate a product like that, so I would have to distribute. So let's distribute. So this is the integral from secant squared dt plus secant t tangent t dt. And not a problem. Which function prime is secant squared?
Tangent.
Very good. Tangent t plus which function prime is secant tangent?
Is it just secant?
Very good. And that's it. You want to check? No problem. Differentiate this, differentiate that, you'll get the same thing. Okay, I'm looking and see what else we have here. Interesting examples. Okay, well, I think we should continue with the last section. I still have the total distance situation, one more, but we can look at the substitution rule. Last section. I still have one thing to show. Substitution rule. Well, why would we ever need to substitute? So for example, if I want to solve this equation, I know it has 4 solutions, but I may not see that this is this. I may or may not. Assuming I don't see this, I notice that I can replace x squared by t because this is t squared. So if I let t be x squared, then the equation I'm looking at now is t squared minus 4t plus t equals 0, and now I should see this one. Solve for t and then come back and solve for x. So the substitution is meant to help. If it gets everything more complicated, then it's not helping and I'm not on the right track. But the substitution in an integral is meant to help us. Okay, so let's see how we address problems that are easily handled with substitutions and not that easily handled without. 32. Oops. 32 on page 414. So you can see how useful. Sine natural log x, sine of natural log x, divided by x dx. So what do I see here is something that bothers me, and what bothers me is, but this is not the mathematical thinking, right? This is the easy way of looking at the problem. What bothers me is this. Why? Because it's inside sine. If I have sine x, I can handle that. But sine of natural log, well, I'm going to say let y be natural log. This is the correct substitution only if dy, the differential of y, is in the problem. Or just the constant is missing. Again, this is the easiest way to approach the substitution rule, I think. So, okay, I denoted natural log by y, but now I need to determine dy. Why am I interested in dy? Because no integral in y can exist without dy. So I want to change this integral from x to something in dy if I can make it easier, but I cannot copy dx when the integral becomes a function, when the integral is applied to a function of y, I cannot copy dx. If this is a function of y, I have to have dy. If this is a function of v, I have to have dv. So I created this function, but I have to determine its dy. And remember, several times we discussed that y prime is not the same with dy. So once I have the function natural log x, can anyone give us the dy of this function? Anyone? I know you know. We used it in differentials, we used it to approximate, we used it all over the place.
Drawing a blank. Sorry.
That's okay. So let's talk about the difference, because this is very important. The difference between the derivative and the function. I'm deleting some videos here for a second so I can make room, more room here on the hard drive. Okay. So if I have, let's say, x cubed, f prime is 3x squared. But dy is f prime of x dx. So then dy will be 3x squared dx. The derivative is 3x squared. The differential of y is 3x squared dx. So then coming back, dy is then what?
So 1 over x dx.
Exactly. That's exactly what I needed you to say. Thank you. So it is 1 over x dx. Now, is this piece in the problem? Yes, it is. I'm going to start from the beginning and writing it one more time. I don't want to go back there. So the integral from sine of natural log divided by x dx. Now, this is sine y. I hope you agree, because I denoted by y natural log x. So now this is sine y. And now I have this piece, dx over x, or 1 over x times dx, which represents what? dy. So from something ugly, I got this. And what is the antiderivative? Which function prime is sine y?
Negative cosine y.
However, this is an indefinite integral. It was given to us in terms of x. The answer must be in terms of x. Not a problem. All I have to do is go back and replace y by natural log x. So then the answer is negative cosine natural log x plus a constant c. At this point, you could say, show me. And I will. I will differentiate both sides, and I guarantee you I'm going to get the same function. Questions? Questions? This is part 3, April 29th. Okay. No, it's not for kids. Yes, make it public. Okay. So let's say I'm going to copy the beginning, which was that. So we have the integral from sine natural log x over x dx, and we came up with negative cosine natural log x plus a constant c, and we're not sure. If we're not sure and we want to check, all we have to do is differentiate both sides. When I differentiate cosine, I get negative sine with minus in front. I get sine natural log x times the inner function prime, which is 1 over x, times c plus c prime, which is 0. So then this side, I get sine natural log x over x. When I differentiate this side, what do I get? I'm differentiating an integral. What is the result on the left?
Just sine natural log x over x.
Exactly. That's how the substitution rule works. Okay, let's look at more examples. Still with the indefinite, and then we'll go to definite. The procedure is slightly different. Okay, I'm looking at 27. Same page, 414. The integral from x squared plus 1, x to the third plus 3x to the fourth dx. Oops, what do I do with this? Okay, so let's think about it. Well, I'm looking at the inside, and I really don't like it, because it has power 4. I don't have anything against this piece. It's just a quadratic function, not a big deal. But of course, I look at this, and I see power